Uh, all right. Hello, everybody. Welcome to the lecture 4 of differential privacy. Today, we're going to finish sparse vector technique and how we are going to be applying sparse vector technique to the linear query release. And then we're going to start a new topic on privacy selection. Okay, so as usual, we'll start by going over the things that we've talked about in the last lecture with a quick recap and revisit some of the trickier stuff that we've learned in the last lecture. So last time one of the things that we did is to generalize the problem of linear query release from just outputting like a linear combination of a bit vector into something that completely covers the statistical query family of problems. So these are the family of queries that's in the form of some function f applied to the individual data point I, and then you sum over I from 1 to n. So we've shown that this can be written as a linear query of some q defined by this f, taking inner product with a histogram or multi-set representation of the data set X. Okay, so yeah, I'm missing 1 over n here since it is normalized. And for this family of problem, we've applied Laplace mechanism to release a sequence of linear queries Q1 to Qk. Yeah, and all of them, again, they are in, say, 0, 1 to the space of the data space. So this X is again is a data space. Say if there are d Boolean features, and this is a vector of 2 to the power of d long. And we've applied what we know Laplace mechanism to this problem in 2 different ways. In the first way, we apply it to just directly add a fresh random noise to each one of these Q1 to Qk. And by releasing these queries and composing over the multiple access to the same data set, that we were able to obtain an error that is on the order of the max error that for all the k queries, we obtain that k over epsilon and log k over delta with probability at least 1 minus delta. So this comes from just using the tail bound on the Laplace random variable and the union bound over all k queries. The reason why we have a linear dependence in k is because we need to split the privacy budget to each one of these queries so that the total privacy loss satisfy epsilon dp. An alternative way of applying Laplace mechanism is to directly release X, right? So instead of releasing this, now we can release X hat equals to X plus Laplace noise. Now this is because L1 sensitivity of the histogram representation of the data is 1, and we don't need to compose over the over the many different coordinates, so we can simply add this to achieve epsilon dp. On the other hand, like once we have this, we still need to answer all these queries. So what we can do is to make use of this synthetic data set and then use qi transpose x hat as our answer to these questions. And by the concentration of this calligraphic X cardinality number of independent random variables and their mean, this converges to qi transpose X, right? So this converges to or in other words, the error is smaller than yeah. I'm also missing 1 over n here. 1 over n epsilon. But since these are a summation of the data space cardinalities number of random variables, so we incur a square root of X cardinality, and then union bound over all random variables. So we got K over delta with probability 1 minus delta. Okay, so they have very different characteristics. So one depends on K, the other depends polynomially on the space of the on the square root of the data space. So neither of them are ideal. So that was why like we were thinking about more advanced algorithm design ideas. And to start, we introduced this idea called sparse vector technique, motivated by the need of selecting a subset of queries from a possibly very large number of queries. And we want to select those queries where the answers are likely to be interesting. And how we consider queries to be interesting is that their values on this particular data set is larger than a particular threshold. Okay, so if the number of queries that are interesting is small, and the hope of sparse vector techniques that we only wanted to pay the spend of our privacy budget on those queries that are interesting, and effectively not spending anything on those that are not so interesting, right? So that's the idea of sparse vector technique. A building block of the sparse vector technique is the so-called above threshold algorithm, above threshold mechanism, which iteratively go over a sequence of queries that say some adversary gives us, and then we add noise to the threshold. We also add Laplace noise to every query before we compare that with a noisy threshold, right? So this can be thought of as a approximation of the screening procedure that you would run otherwise without the privacy concern. And what we the little bit of generalization that we add to this is, instead of just adding Laplace noise, we are using an arbitrary noise adding mechanism that could add other noise. So as long as this noise mechanism M1 and M2, so M1 adds noise to the threshold and M2 adds noise to this individual query. So as long as these two satisfy say half epsilon dp for all queries with sensitivity 1 and all queries with sensitivity 2 respectively, then this above threshold mechanism satisfies epsilon dp. Okay, so one particular property of this is that it doesn't restrict on how long this sequence of queries is likely to be. We can screen as a potentially unbounded number of queries before we get one that is interesting, and that costs us only like 1 unit of the privacy budget, right? So that's an interesting property of this algorithm, and the sparse vector technique is effectively just a composition of C such above threshold, and when we specify the a maximum number of discoveries to be a integer C, then we can allocate one C of the given privacy budget to each above threshold algorithm. So overall, this algorithm is epsilon dp. Okay, towards the end of the last lecture, we analyzed the above threshold algorithm on how it works and how possibly it could like in some sense release a sequence of queries like notice that the above threshold output only the top and perp, where perp indicates not so interesting and top indicates interesting, right? So it doesn't actually output the numerical value of FID plus noise, but rather it outputs a selection of still like outputting a bit vector that is arbitrarily long while spending only like 1 unit of privacy budget is somewhat remarkable. So we analyze above threshold by first finding an equivalent representation of its output, because its output can be represented always as this form, and it's completely described by this integer k, right? So this integer k is a random stopping condition, and whenever we know k, we know that the output looks like this. Okay, and we can also, by redefining the queries, so that we can always just assume that the threshold is equal to 0 without loss of generality. So then we can proceed with the proof by first rewriting the output of the above threshold algorithm to be equal to k by condition on the threshold noise, but condition on the value of the threshold noise, and condition on this noise, and then we can more easily write down the conditional expression of the conditional distribution of how the rest of the noise should behave such that the answer is K, right? And this is really that for all the i's that are smaller or equal to K, and the noise is like not sufficiently large such that this query plus the noise is above the noisy threshold. So notice that this is 0 plus Z. This is noisy threshold. So this basically checks the condition of the algorithm. And the second term would be like the last one happens to be above threshold, right? So that's a direct translation of how the algorithm works if we end up getting an output of K. And then we can like just rewrite this as an integral form and over the different noise random variables. So this is a threshold noise and this new I. So they are the random variables that got added to the individual queries as we do this noisy screening. Okay, and the key trick over here to get everything to work is in some sense a shifting operation that redefines a random variable with a change of with a change of variable. So if we define U to be Z plus this delta, and Z plus delta is a global sensitivity. So in this case, it's 1. Then we can basically by redefining this and then multiply and dividing this everywhere, and then we can rewrite it as something that's shifted, and that shifting applies to all the components of this product, so that the regions of this integral shifted a little bit by delta. And the point is that by doing this, the first term, this is what we've explained last time. The first term, so this is a density ratio of the threshold noise, and we can think about it as I guess this is the Z random variable. Z random variable is equal to the little z minus delta, and if we move this to the other side, this is delta plus Z is equal to Z. And the denominator is a P, the probability of this random variable being equal to Z itself, right? And this is the same as 0 plus the random variable is equal to Z, right? So if we consider a trivial query where the query output 0 for one data set and the query output delta for a neighboring data set, then by the assumption that this Z like is epsilon differential, half epsilon differential private, we know that this ratio is smaller than e to the power of half epsilon, right? So that's how we bound the first term. And then like we can just redefine this U to be Z again, and this becomes like the standard kind of expectation that we're hoping to get. Then the second term is what is interesting. The second term basically says that the probability of like this noise random variable nu I is smaller than Z minus delta plus Qi of D. Right? If we move things a little bit, if we move this Qi to the other side, and this is the same as P of nu I plus Qid, right? So this is our noise perturbation algorithm to perturb this Qi. So this is smaller than this is smaller than this this plus delta is smaller than Z. Right, and one can argue that since the perturbation of this Qid to Qid prime is always within plus and minus delta to this is always smaller than P of nu I plus Qi, and D prime smaller than D. Yeah, you can check that this interval is always larger than this interval. Therefore, this probability inequality is true for all I. Like no matter how many of I that you multiply here in the second term, we can always just directly bound this by something that's defined by this alternative neighboring data set D prime. Okay, so that's the key idea behind how this can possibly handle an unbounded number of queries. So K can be arbitrarily large. Meanwhile, due to the shifting, we've make sure that the middle term that has all this product of probability distributions always satisfy this inequality. Therefore, it doesn't depend on how large this K is. So it remains to deal with the last term, which I covered a little bit, but didn't cover it very carefully because we were running out of time. So let me do it more properly today. So the key idea is that we want to somehow connect this probability distribution that depends on the data set D, and connect that to the like in some sense bound this by a related probability distribution that's defined by a neighboring data set D prime. Okay, and the questions are how we go from the left hand side to the right hand side. What we can do is the following. So first of all, let's rewrite what they mean. So this means that I guess nu K plus 1 is smaller, is larger than Z minus delta minus Q K plus 1 D. And we move this to the other side, this becomes I guess Q K plus 1 D plus delta plus nu of K plus 1, this one being larger than Z. Right, so these two are exactly the same, and what we can do is to define this, yeah, like I guess similarly on the right hand side, this is also equal to the probability of Q K plus 1 now D prime plus nu K plus 1, this one being larger than Z. Okay, so what we can do is to define so-called a fictitious query or some utility query that only exists in theory. We can define this Q tilde with an arbitrary input data set D tilde such that whenever this D tilde is equal to D, then we output QK plus 1D plus this sensitivity delta. And whenever this D prime is not equal to D, then we just output KQ plus 1 D tilde. Okay, so what this means is that this part of the expression, I can write it as a Q tilde of D. And this part of expression, I can also write it as a Q tilde of D prime. Right, so this is otherwise case, and this is a if D tilde is equal to D case. Now the left hand side and right hand side becomes like a probability, becomes the same event of the same query, but just with two data set being neighboring. Okay, so it remains to calculate the sensitivity of Q tilde, right? So what is the sensitivity of Q tilde? Can anyone shout it out? Exactly, the answer is 2 delta. The global sensitivity of Q tilde is 2 delta, because for any data set D tilde that's not equal to D, then it is smaller than 1, because QK plus 1 has a global sensitivity of 1. On the other hand, whenever one of the two neighboring data set involve D, then you have this additional delta that's occurring. Therefore, it increases the sensitivity to 2 delta, and that's also the global sensitivity for all cases. Okay, now like it remains to check the condition by applying our assumption on this noise nu K plus 1. So nu K plus 1 is coming from a noise adding mechanism that satisfy epsilon half epsilon dp that satisfy half epsilon dp for all queries with global sensitivity smaller than 2 delta. Right. Therefore, because of this, we can bound the left hand side with e to the power of half epsilon the right hand side. Okay, and that deals with the last term. So we'll have e to the power of half epsilon and the probability of qk plus 1, d tilde being smaller than being larger than z. Okay, and if we collect this and that and the one in the one in the middle, and everything got connected together, and that checks the same definition here, but with d replaced by d prime, right? So altogether, this gives us p of m d is equal to k for any k is smaller than e to the power of epsilon. P of m d prime is equal to k. Therefore, above threshold satisfy epsilon differential privacy. Okay, this is a very delicate like argument to prove something that's highly non-trivial, and I hope I've explained it clearly, like this time, like with some more time to delve into how we define this utility query. Q tilde. Yeah. Any questions here? How do I get e to the this one? Oh, based on the assumption that here that we are adding this noise, and this noise satisfy is coming from a noise adding mechanism that satisfy half epsilon dp with sensitivity 2, right? So that's coming from the definition and how the algorithm works. Okay, so by shifting this by delta, like using that change of variable, what this does is that it's allowing us to bound all k-1 queries with without costing anything, and the real cost is only in the last step, and it's once and for all. Like for that, we need to pay twice. So basically, by paying twice, we in exchange we get a benefit of we get a benefit of being able to answer everything for arbitrarily large k. Okay, so that was from the last topic of the last lecture. So today we're going to finish the topic of sparse vector technique by analyzing its utility and applying sparse vector technique to answer many linear queries, actually exponentially many linear queries, using an algorithm called private multiplicative weights updates. And once, so that's a big part of today's lecture. And towards the very end, I'll give a gentle introduction to the problem of differential privacy selection and cover like exponential mechanism. And we'll leave report noisy max for the next lecture. Okay, that's a plan for today. Yeah, here's the reading materials behind today's lecture. So I encourage you to read a subset of these if you find today's materials interesting. In particular, so I'll be making use of like a classical result that's from online convex optimization or online learning called multiplicative weight update, or HATCH. Those who have taken my course on convex optimization, like you should be familiar with this algorithm already. But we'll use this as a black box today. And for those who are interested how this black box work, you can go to these references or watch my video from convex optimization. All right. So the first thing that we'll analyze is the utility of the sparse vector algorithm. Like how should we even think about the utility of the sparse vector algorithm? So it is a selection algorithm. It selects out of a online sequence of queries and select a subset of them that are interesting. So we can define the utility to be whether we are able to so among those things that we discovered, among those outputs that are tops, are they truly interesting? And also we can talk about no false discovery. So among those that we reject, that we deemed not so interesting, like can we certify that they are really far from being interesting, or they cannot be very interesting. Okay, so that's like the kind of utility guarantee that we're going to talk about for this sparse vector. And idea is really to look at all the random variables in the system. So they are basically a bunch of Laplace random variables, right? So we have a bunch of Laplace random variables, and we can bound all of them with a Laplace tail bound that we learned from the last lecture. To begin, so how many times are we adding to the threshold? So again, sparse vector is a composition of C different a composition of C above threshold, and in each above threshold algorithm, we're adding to the threshold for just once. Okay, so there are C Laplace random variables, Laplace RVs with a parameter I guess C2C over epsilon. And there are also, let's say that in total, the sequence is K, a sequence of K random variables, so K queries. So there are also K Laplace random variables that we add to the queries themselves. So these are 4C over epsilon. Yeah, this is 4C over epsilon random variables. So, but by the Laplace by the tail bound of the Laplace random variable, which we learned in the last lecture. So this says that the absolute value of Laplace random variable being larger than e to the power of minus t over b. Larger than t is smaller than e to the power of minus t over b. Right, so if we just apply this and then take a union bound for all these random variables, then we can get that for all of them. So all the random variables they satisfy their error is smaller than their error is smaller than, let's take the larger of the two, so 4C over epsilon. And log, let's say C is smaller than K, so 2K over delta with probability 1 minus delta. Okay, so now that we have this, we can use this to show that all true discoveries are like sufficiently interesting, and all those rejections are not that like overly interesting. So by first writing down the decision rule. So the decision rule is that this Q transpose X minus Q transpose X minus some threshold T is plus noise Qi minus nu I is larger than T plus Z. Right, so for one of the above threshold, this is a formula, and using this error bound, which bounds the absolute value of nu j and z, we get that with high probability. So for all those where we output top. Then this means that QITX is actually larger than T minus 8C over epsilon log 2K minus delta, right? So this is saying that all these discoveries are at least like marginally passing the bar of being interesting. And now for all those I where we output is perp, this is an indicator for things that are being not so interesting. Like by using the rule of the by using the same rule here, and we can show that this Qi transpose X is Qi transpose X is smaller than T t plus 8c over epsilon log 2k plus delta. Okay, so this says that among those that our output is perp that we reject, like it cannot be too much above the threshold, right? It's approximate version of these screening rules, and like these errors are needed, and we cannot really tell for sure whether a QI transpose X is exactly at T or slightly bigger than T or slightly smaller than T. But what these rules is telling us that if this QI transpose T is way larger than T, then it will be selected. And if this query is substantially smaller than T, then it won't be selected. Okay. Yeah, and we've already taken the union bound over all these Laplace random variables. Yeah, we'll see how we can apply this when we get to using the sparse vector for releasing many linear queries. But before that, there is an issue about the sparse with the sparse vector technique that we use that we've talked about earlier, because this algorithm is really not outputting the actual numerical values of the query, right? So we can select a subset of these queries. But we're not actually reviewing the actual values of them. We're only screening them, and it gives us a bit vector that selects those interesting ones among those among all of them. So what we can do is to interlace like one Laplace mechanism after every above threshold. Right, so after running above threshold, then it gives me a discovery, and then for that discovery, then I'm just running Laplace mechanism to release the value of that query that I select from the above threshold, and then I continue with the sparse threshold, and you can see that this is a composition of 2 C mechanisms rather than C mechanisms. So by doubling my privacy budget or doubling the size of my noise on each one of them, then I'm able to also output the numerical values for those interesting ones. Okay, so one observation about this mechanism about this is that we don't actually know like which Laplace mechanism to use before finish running this above threshold one. Because this above threshold will select a particular query, and it is on that query that we're running this Laplace mechanism, right? So this is one instance of so-called adaptive composition or interactive composition, where the sequence of mechanism that we select is a function of the output of the previous mechanism that we choose. Yeah, the distinction of that will get clearer in I think in the next lecture. But for now, like let's appreciate the fact that the composition theorem in differential privacy actually allows us to handle adaptive composition. So this kind of thing could work. Okay. So now let me explain the idea of how we can apply the sparse vector technique for online query release of answering many linear queries. So let's set up the problem. Like a online query release is a problem setting where there's some data analyst or some adversary who comes up with a sequence of linear queries. Let's say that someone is doing the exploratory data analysis on a very sensitive data set. And you as a curator of this data set have to provide like more or less accurate answers to all the questions that this data analyst asks. And meanwhile, based on your answers, the data analyst could come up with the next question to ask, right? So you have a sequence of linear queries, Q1, Q2, Qk, and each one of them could depend on the answers that you gave based on, say the answers are A1, A2 to AK, right? And then Qi could be chosen as a function of Q1, A1, Q2, A2, all the way to Qk minus 1, AK minus 1, right? So Q1, Qi, yeah, I minus 1 can be adaptively chosen. And we have two baselines for this, right, that we have already explained. And for the Laplace mechanism, of just keep releasing the one that's given to me with independent Laplace noise, then it depends linearly on Q. I'm like ignoring the log factor. And also for normalized queries, say average query rather than summation query, then the sensitivity is 1 over n, and then you can add those 1 over n multiplier here, right? So whether it is normalized or not, sometimes I'm not being very careful in making everything consistent. But the ballpark is so far away from each other. And then when I explain the comparison of those results, and you can add that 1 over n or remove that 1 over n to jump back and forth between normalized linear query and the unnormalized linear queries. Okay, on this slide, I'm showing unnormalized linear queries. And the alternative approach of applying Laplace mechanism to release a whole data set, or the histogram, or the contingency table. So these are, I use them as synonyms. You get a square root of x in the space of the data, but the improvement is that you get an exponential improvement over the number of queries that you can answer. Okay, so the goal of the algorithm design with sparse vector is that we're hoping to get a polylog dependence on both the cardinality of the query space and the size of the data space. Okay, then it gets the best of both worlds. And the idea of doing that is to couple the kind of noise that you're adding. So instead of using independent noise, which allows adversary to average out the answers that she gets, and then get the more precise understanding and like more precise number about the data. Like now let's use correlated noise, and it's a particular way of using correlated noise by constructing a synthetic data on the fly. Right, a synthetic data is something that we publish differentially privately on the fly rather than like upfront at the beginning. So how we are using the sparse vector technique is the following. So for an online sequence of queries that we receive, we'll just keep running above threshold. And the above threshold is run to a particular type of query, which measures whether the answers that are coming from the current synthetic data is accurately enough comparing to the ground truth. So this error is, let's say that my synthetic data set is x tilde, and the actual data set is x, actual data set and synthetic data set. Okay, and this error is defined to be this q transpose x tilde minus q transpose x. So that's the absolute value difference of this error. And this is something that satisfies bounded L1 sensitivity. It's just a scalar, and its sensitivity in this case is 1, right? So I can apply the above threshold method to this query and to check whether this is larger than, say, alpha. If this is larger than alpha, then I know my synthetic data is not accurate, and I'll just go to my actual data and then output an answer from the actual data using Laplace mechanism. On the other hand, if this answer is already sufficiently accurate, then by above threshold, it's not costing me anything, right? Then I'll just make use of this already the synthetic data that I already have, and then output q transpose x tilde. Okay, so that's the idea. If we can show that the synthetic data set will take only a small number of actual the private releases from the actual data to learn to perform really well, and then if we can show that the number of times that we have to update the synthetic data is somewhat small, then that allows me to save my privacy budget. So the kind of noise that we add are correlated in a sense that they're correlated through a synthetic data set that I learned on the fly, and this synthetic data set depends on the previously released queries. So to think about them as the training data for this synthetic data set. And once I get the synthetic data set, my output that's coming from the synthetic data set will be correlated with the noise that got added to previous queries. So in some sense, this allows the method to generalize to future queries using those queries, answers to those queries that we've seen so far. Okay, so that's a high level idea. So whenever we release a query, then above threshold algorithm stops, and then we'll restart it by say re-randomizing the threshold and so on. So we have a more precise pseudocode momentarily. But before that, I need to introduce like a black box that we're going to be using to make the previous idea happen, right? So this is a like family of research, a family of algorithm called no regret online learning. So in particular, this is the most basic version of online learning called learning from expert advice. So let me explain how this setting works. Just imagine that you are a stock trader and you are looking at the news and looking at all these review articles to tell you about the stock choices, which stock to buy, and whether they imagine that in tomorrow this stock prices will go up or go down, right? As a concrete example, let's say that I'm getting the stock advices from Dan and from Ming and from Rachel and from say my cat Raffles. Okay, and in day one, Dan said that go buy Tesla, and it's gonna go up, and Ming said that buy Google is gonna go up, and sell everything else, and Rachel says just hold everything that you hold everything you have, and then keep it to and keep all the Facebook stock that you have, because that's something that's going to rise. And Raffles, my cat Raffles, basically put his paw on the GameStop and say yeah, that's his best bet. And after day one, like the results comes out, and Tesla rises by 1%, Google is down by 2%, and Facebook is up by 5%, but the GameStop is up by 49%. Okay, and that's the kind of outcome that I get. And then there are day 2 and day 3 and all the way to day T. And after each day, I receive the outcome for every choices that this expert had made, that I can evaluate them to see who performed well and who performed poorly. And these numbers translate into either rewards or noise or losses that these experts has incurred. Okay, and the goal of learning is that I want to come up with a strategy where I can somehow learn an ensemble model of all these 4 experts that I get based on their daily losses of return, the daily gain and losses that's reviewed after that day. And can I come up with a strategy that does as well as the best expert in the hindsight? So that's the idea. So let's say that my strategy is that I pick x1 to xt, and each one of these x1 to xt is a probability distribution out of these 4 experts. Okay, so I'm coming from this probability distribution of the expert space, and what is my performance going to be like? And yeah, and by the way, the vector of losses for individual expert at time t is, say, in 0 to 1 to the power of 4, right? So after every day, like each expert would incur a loss, which is a numerical value that's between 0 and 1, and my regret is going like so. First of all, my performance. Suppose I split my capital into believing 50% believing Dan, 20% believing Ming, and 30% believing Rachel, and none on Raffles. Then the regret is defined as sum from the day 1 to day T, my choice inner product with a return, inner product with a loss, and this is my loss, my cumulative loss, Now I'm comparing that with the best expert in the hindsight. So this means that the best individual, one of them, LT, in the hindsight, T. Yeah, after T step, I look at the track record. It turns out that Raffles performs the best, right? So then this is saying that I want my regret to be little o, little ot. Little ot means that as t gets larger, needs to be sublinear in the time horizon. As t gets larger, my loss is on average, if you divide both sides by 1 over t, it converges to the performance of that of the best expert. Right, so it's a modest learning goal, and then we say that whenever this is sublinear in t, whenever the regret is sublinear in t, then this is called a no regret or asymptotically no regret learning algorithm. So this is a cumulative loss of the best expert. Okay, specifically, there is actually an algorithm that gives us asymptotically no regret. This algorithm is called patch or randomized multiplicative weight algorithm. So let's go over this, how this algorithm works. So initially at time 1, I don't have any knowledge about how these experts would perform. So I'm assigning a weight of 1 for each one of them. Okay. So after then my strategy is going to be just to do a weighted averages of the strategies that's coming from each expert. So this, like line 3 says that sample this with probability. So this is a case when you can only pick one of the expert and you can randomize it. So effectively you are picking a mixture in expectation. But in the stock trading example, we can actually mix the strategies and average them, and then that becomes a valid strategy as well. So in this case, we can simply predict the weighted average. Yeah, we can simply set this xt to be the weighted average rather than sample with the probability being xt, right? So we can pick xt when xt is equal to this. And after that, I incur a loss lt of xt, which is equals to lt transpose xt. And notice that xt is a probability distribution, right? So this is the same as the expected value of this incurred loss. Now that I've incurred the loss, I look at each expert and take a look at the expert that each expert has incurred. If you incurred a larger noise, I'm going to discount your credibility a little bit more. And if you incurred a smaller amount of loss, then I discount your credibility a little bit smaller. So I do this is in the exponential fashion with this epsilon being the learning rate. Right, so I make your credibility half as small if your prediction is terribly wrong, and if your prediction is only a little bit wrong, and then I discount your credibility a little bit smaller. And after doing that, I update my weights, and then I renormalize it into a probability distribution, and that is the strategy that I'm going to be taking for the next step. Okay, this is an algorithm that makes intuitive sense. I won't try to prove to you why this works. Like watch my video or check out this textbook. So the proof is somewhat short, but what you can show is that the regret, that is a difference of your performance and the performance of the best expert in the hindsight, is bounded by these two quantities. It's bounded by the sum of these two quantities, where n is the total number of experts. And this is xt transpose of lt square, and we can simply bound this by the L infinity norm of lt square, that is 1, and by the L1 norm of xt. So notice that it's a probability distribution. So this gives me 1, right? So the whole thing gives me epsilon times t. So what I have is a epsilon t plus log of n epsilon, and by choosing this epsilon optimally, and I can get 2 times square root of t log n, right? So the key takeaway is that this is logarithmic dependent on the number of experts, and then it is a sublinear in T. Therefore, this is a no regret learning algorithm, and it depends only on the square root of T. Okay, with that in mind, let's move forward. Yeah, actually, before that, like there is an important corollary that we'll be using. Say the previous theorem says that we can compete with the best expert in the hindsight, right? But we can actually also compete with the best proportion of probability distributions in the hindsight. We can compete with any mixture of these experts in the hindsight. It follows from a trivial argument. So notice that this I star can be anything. It doesn't have to be the one that minimizes the cumulative losses. It can be anything, and this inequality works. So what we can do is to take this I star to be Dan, and take this I star to be Ming, and to be Rachel, and Raffles, and multiply like my favorite probability distribution among them. So P of Dan, P of Ming, and P of Raffles, and multiply this on the left-hand side and right-hand side of the above inequality, and then just add them up. So you'll see that this is a constant that has nothing to do with the probability, and this is also a constant that has nothing to do with the probability, and they will all give me the same number, but the one in the middle becomes the one in the middle becomes the weighted averages of the performance of these experts in the hindsight. Right, so let's say I have this fixed probability comparator P, and what this says is that my performance is smaller than sum of the P transpose of LT plus 2T log of N. Okay, so this is the upper bound of the regret against the like arbitrary probability distribution of the expert. Okay, now like with this corollary, let's try making use of this to let's try making use of this to apply to the linear query release, and we'll do that with a one step at a time. Like let's do that first without adding privacy constraint. Okay, like since the multiplicative weight update or the hash updates like operates on my strategies that are fraction between 0 and 1, so it operates on the probability distribution. Let's now like switch the gear a little bit and consider the normalized linear query, right? So when we consider the normalized linear query, the true data, let's define this to be P. So this is our comparator, and the initial synthetic data, like recall that the multiplicative weight choose it to be uniform and then normalize. And let's choose it to be 1 over the cardinality of the data space. And so what are these experts? These experts are the like vertices of this this data space. So each individual possibility of this data set is an expert, right? So what we're going to do is to take a sequence of online sequence of queries. And for each query queue, let's try, like as we said earlier, let's check whether this is larger than alpha or not. If this is larger, if this is smaller than alpha, then let's just output the synthetic version of the output. Like if this is larger than alpha, then we know that outputting this is not going to work. So we'll output the true value. After we output the true value, let's design this particular choice of the loss vector and then pass back into the multiplicative weight algorithm. So this is the most interesting part. So the choice of this loss vector, first of all, the direction of this is proportional to this linear query, and then I'm multiplying this sign here. So just now I said the loss is between 0 and 1. So the same argument would apply to the cases when loss is between -1 and 1, right? So I use the Holder's inequality. So let's take this slight generalization of the of the setting, so that this is a valid choice. And yeah, we'll see why this works. But then once we have this loss, we can make use of the update rule to the hash algorithm by doing the multiplicative updates, right? So now I'm discounting the credibility of this individual expert exponentially with this eta chosen to be this learning rate. Okay, and then we increment t, and t is the index of the number of times this online learning algorithm has been called. Okay, so that's basically the algorithm, and how do we make sense of it? So first of all, I argue that for this learning algorithm, the error, like for this algorithm, the error is always smaller than alpha. So there are just two cases. The first case that we output this, and this only happens when this is alpha close to the ground truth. When the synthetic data gives me something that's already accurate. And when it is not accurate, when this p tilde is not accurate, now I'm outputting the ground truth itself with error 0. So therefore, this algorithm always outputs like answers to these queries with error at most alpha. Okay, does that make sense to everybody? Good. With that, so now the interesting part is that now we can take the regret bound of this multiplicative update algorithm as a black box and see what's the implication on the number of iterations that we have to run this algorithm. Okay, so let's try plugging in the choices that we had before. So what are these XTs? These XTs are just our p tilde t. So this is a current synthetic data. So we'll have p tilde transpose LT. This is smaller than, so like we'll be using the version of the comparator where we're comparing with a fixed proportion, right? We've shown that this is okay from that corollary. So let's take that proportion to be the ground truth data. To be the proportion of the ground truth data in a data space. So this is T from 1 to T, P transpose LT. And we'll use upper bound of this regret, and we'll choose the learning rate appropriately so that we end up getting 2 times T and log cardinality of the data space. Okay, I'm just applying this regret bound. And the next thing that we should do is to substitute the definition of this LT. Let's move this to the left-hand side first. Minus P transpose L transpose LT. And what is LT? LT is a sign of this quantity. So LT is a So this is a sign of so Q times the sign of PT tilde transpose Q minus P transpose Q, right? So the sign of this quantity multiplied with itself, what does this give me? It gives me the absolute value. Right, so when this term is positive, then this sign is positive. When this term is negative, this sign is negative. So the product of them gives me the absolute value. So I'll get P tilde T minus P transpose Q absolute value. And this is the error of my P tilde T. Okay, and so what this says is that the sum of error that my multiplicative weight update algorithm in every iteration is smaller than 2 square root of T log of cardinality of X. But when are we calling this algorithm? Like we're doing this kind of screening, that we're only calling this algorithm when the error is larger than alpha. Therefore, there's also a lower bound of this error that it is larger than T times alpha. Okay, what does this imply? It implies that T must be small. Like this algorithm finishes with probability 1, and then there are no more queries that we ask of this this algorithm. And in the remaining calls of this algorithm, indefinitely, you'll always keep invoking the synthetic data. Right. So what this gives us is let's divide both sides by square root of T and also by alpha. So square root of T is smaller than 2 times log X cardinality over alpha, or rather T is smaller than 4 log cardinality of X over alpha squared. So this shows that the total number of iterations of the multiplicative weight algorithm that we run needs to be small, needs to be something proportional to 1 over alpha square, where alpha square is error. Alpha is a desired error. Okay, so now yeah, we'll take a break for 5 minutes, and then we'll resume at 2:07, and then we'll talk about how we can just revise this algorithm into the differentially private version of this algorithm, and then use the same argument to show that this actually works. All right, everybody, let's get back to our seat and we'll start the second half of our lecture. Yeah, so one of the interesting thing of this application is that we are choosing this LT, we're choosing this loss vector as a function of the as a function of the player's choice, as a function of the player's choice of XT, right? So this is allowed in online learning because in online learning, the adversary is a fully adversarial setting, so it can depend on the choices of the player's actions, and I guess so that generality is not typically used in the standard machine learning when the data are IID. But in this case, like we're actually making use of the full generality of the power of adversarial online learning when the loss vector can be reactive to this particular choice of PT that you choose, right? So it's coming from this sign, right? This sign thing. So when your error is positive, then I'm making this loss positive. Otherwise, I'm making this loss negative. Yeah. So it's kind of cool that this choice actually works in this case and gives us the ability to construct the regret to be just the sum of the sum of the absolute value losses of the prediction versus the ground truth. Okay, now let's try to modify this algorithm with sparse vector technique and Laplace mechanism to try to make this a differentially private online query release. Yeah, so the like it still goes by that we want to like normalize the data and deal with a normalized linear query. So in this case, instead of being able to do the exact thresholding, now we'll have to use above threshold for this, right? And instead of just outputting Q transpose P directly, we can't because it's a violation of the privacy guarantee, and we need to somehow add noise to this. And then the only techniques that we know how to do it is to use Laplace mechanism. And for this Laplace mechanism, then this query has a global sensitivity of 1/n. And for the above threshold, this threshold also have the global sensitivity of 1/n. Right? So take this absolute value of the two different things, and then Q transpose P is the only part that's coming from the data. And by adding or removing one individual data point, it can at most change this absolute value by 1/n. Okay, and then the same output from this Laplace mechanism is used to replace this quantity. And substitute in the sign to construct this loss vector. Yeah, so the key idea of the analysis is to show that this actually works. Okay, so more specifically, but by using this numerical sparse vector and Laplace mechanism, what it boils down is just to add noise to the threshold. So we'll add noise to the threshold each time this this above threshold algorithm is initialized. So now the threshold is alpha hat, right? So recall the sensitivity is 1/n. So this is a red parameter. And epsilon0 is not really the total privacy budget of interest, but let's just set this epsilon0 as some parameter that we're gonna figure out its values like momentarily. So currently just say that this is a unit privacy loss in every iteration of the call of the multiplicative weight algorithm that we will have to incur. Okay, so we perturb the threshold, we perturb the query, which is the absolute value. And then if it is above the threshold by this noisy decision rule, then we will release this Y transpose P. And this released value will be used in constructing the loss vector for the online learning algorithm. And then we update the online learning algorithm using multiplicative weight rules. And one thing that we need to add is for this algorithm to finish before it hit our privacy budget. So we need to set a global upper bound capital N so that so that the whole thing will stop if T reaches N. Okay, so in this way, we'll see how that allows us to achieve like a epsilon differential privacy for all possible for all possible input data and all possible realization of this algorithm. And if we if for one of the queries that it is above the threshold, then I need to restart the above threshold algorithm by refreshing the threshold noise. Yeah, each time we enter this if. Else, then this is the case when the above threshold will output perp. So this is the case when the error is approximately small. Then we're gonna just use the synthetic data to give you the output. So same algorithm, but with noise added here and there, so that we make use of our algorithm design tool to make this algorithm differentially private. The privacy analysis of this algorithm is quite straightforward. So it is simply so in every iteration of this algorithm is above threshold plus Laplace mechanism, right? So by our choices of this epsilon zero of the size of the Laplace noise, then we know that this above threshold is epsilon zero dp, and this Laplace mechanism is also epsilon zero dp. Since we're stopping at n rounds of this algorithm, so in total, the total privacy loss is bounded by 2 times n epsilon zero. So this is a total privacy loss. And we could choose these parameters n and epsilon zero such that the product multiplied by 2 is equal to some predefined privacy budget. Okay, the question is that like this doesn't really give me like which n to choose and which epsilon zero to choose, right? So there are multiple choices of the n epsilon zero that gives rise to this upper bound of epsilon budget, and yeah, so we'll have to choose it carefully so that the accuracy criteria is met, and we need to choose it carefully such that like the algorithm is giving me the most accurate answer possible. Okay, so we'll see we'll see like which particular pair of this n epsilon will work by just working out the utility analysis of the algorithm. Okay, so now let's move on to the utility analysis. Like similar to our analysis of the sparse vector utility, the beginning point of analyzing this algorithm is to first de-randomize by hiding all those undesirable events in a small probability failure of delta, and so that everything becomes deterministic, and then we can use inequality to argue about the outcome that will happen with high probability. Okay, so we start by counting. Say, let's run this algorithm to answer an online sequence of queries that are that are at most k, right? So let's say that there are online sequence of queries that are at most k. So how many Laplace random variables are there in total? Yeah, we can look at the algorithm, and then you guys can do the counting for me. So there are two numbers that are relevant. So first of all, the online learning algorithm is invoked by at most n times, but the total number of queries that this adverbary select is smaller than k. So how many Laplace random variables are there in total? Anyone? So each time this t increment, we need to refresh the threshold noise. So that's one Laplace, that's n Laplace random variable. And for every query that we receive, we'll have to add noise and within this if statement, right? So that's up to k Laplace random variables. And in addition, so each time this one is above threshold, which it is above threshold for at most n times, then this private release of this query by looking at the actual data is also at most n times. So in total, there are at most 2n plus k like Laplace random variables, and the largest one of them all is this one with a constant of 4 on top. Okay, so there are a total of 2n plus k Laplace random variables, and the largest of them has a b parameter being 4 over epsilon 0, right? Let's check for sure. Yeah, 4 over n epsilon 0. So what this says is that for all Laplace random variables with probability 1 minus delta, and for all of them has this, let's say that this random variable is z, satisfy that it is smaller than this multiplied with the log 2n plus k over delta by union bound, right? So for all of them at the same time, and we can a priori provide a high probability bound to say that all these random variables are smaller than this quantity. And for a simplifying assumption, since n is almost always larger, always smaller than k, like n is obviously smaller than k, right? So I can bound this 2n plus k by 3k. Right? I can always do this because the total number of queries that are above the threshold must be smaller than the total number of queries. Okay, so this becomes 4 over n epsilon 0 log 3k over delta. So I call this say yeah, let's not worry about defining this to be something else. Let's keep it. And then the next thing that we'd like to show is that all that is not selected are getting accurate answers, and also all that is selected are also getting accurate answers, right? And the accuracy is some perturbed version of that threshold. So by the selection rule of the SVT. So the rule is that this Q transpose P tilde T minus Q transpose of P, this absolute value is smaller than if it is not selected, meaning that if it is not above threshold, then it satisfies that this plus the query noise nu. So this is it's nu I. Nu I is smaller than alpha hat, and alpha hat is our choice of alpha plus this threshold noise z. So now that we know both z and nu I, they are bounded by this quantity, then this implies that by moving everything to the right hand side, then I guess perp implies that the error of P tilde T minus QI TP is smaller than alpha plus an upper bound of Z and the lower bound of nu, since they have bounded since they have bounded absolute value. So this is absolute value of Z plus nu I, and smaller than alpha plus 8 over n epsilon 0 log of 3k over delta. Okay, so your error is this large. And why does this matter? Because once the choice is this query is not selected, we don't think it's above threshold, then our output is simply to use the synthetic data, so p tilde t, right? And what this shows is that the synthetic data is accurate. It is smaller than this quantity. So next, we'll show that all that is not selected, all that is selected, which is above threshold, are also getting accurate answers. So the rule for this to happen is a qi transpose p minus qi transpose p plus nu I is larger or equal to alpha plus z, right? And what this says is that my output is going to be top. And what this gonna say is that the actual output that I return as an answer from my my curator algorithm is going to be a perturbed version of the ground truth. So we'll do qt transpose p plus this additional noise. So I'll call it maybe call it w. Okay, and since we know w has bounded absolute value from step 1 of this analysis, then qtp minus yeah, so I guess so w's absolute value is simply the error, right? So the error is smaller than, again, 4 over n epsilon 0 log 3k over delta. Okay, so we've shown that in both cases the algorithm is returning sufficiently accurate answer. Like one is smaller than alpha plus this, where alpha is a threshold, and the other is just proportional to the scale of the noise. So what this is saying is that we should probably choose this epsilon 0 such that this absolute value error of these Laplace random variables are proportional to alpha. For instance, let's say that we should choose this such that this is smaller than half alpha. We will choose epsilon 0 such that this is true. Okay, and next, like we will need to check that the total number of times we run multiplicative weights is also somewhat small by looking at the regret bound, right? So now let's look at the regret bound. So the regret is equal to p tilde transpose LT minus my ground truth p transpose LT, and this is equal to by substituting what LT is, p tilde minus p transpose Q multiply with the sign of p tilde t transpose Q minus p transpose Q plus noise W, right? And this W is a Laplace noise that we add, and we know that this W is somewhat small. But like now what we're going to show is that this sign is the same as the sign suppose the noise is not there. When would that happen? That happens when the p tilde transpose Q and p transpose Q, they are sufficiently far away from each other. Then if we add a bounded amount of noise to it, then this noise is not going to change the sign of their differences. So that's the idea, and that actually happens because when are we going to run this multiplicative weight algorithm? So we are only going to run this multiplicative algorithm when this when this output is selected. And when this output is selected, then we know that this inequality is actually true, right? So to say it differently, from the condition that we are actually running this multiplicative weight algorithm, condition on condition on the output being top, this says that Q transpose P tilde T minus Q transpose P, this thing needs to be larger than alpha plus Z minus nu I, right? And this is larger than this is larger than by like requiring by requiring this to be strictly smaller than half alpha, by requiring this bound to be strictly smaller than half alpha, this is strictly larger than 0, because there are 2 copies of the noise, and each one of them is strictly smaller than half alpha, so it's not going to change the, it's not going to make this absolute value smaller. Actually, I need a little bit more than that. I need this to be larger than half of alpha. Therefore, I can I'll still have something so that this margin of error for this W will not change the sign of these 2 things. So what I'm gonna do instead is to replace this half alpha with alpha over 4. Okay, let's replace this with alpha over 4. Therefore, this is strictly larger than half alpha. And because this is strictly larger than half alpha, then adding noise to this before taking the sign will not really change the sign at all, since the noise is smaller than a quarter of alpha. Okay, so under this condition, this implies that the sign of P tilde transpose Q minus P tilde Q plus minus this W noise is going to be the same as the sign of P tilde transpose Q minus P transpose of Q. And when we substitute this back to this equation, and then we get the same thing that we have in the noiseless case, that this is simply the absolute value minus P transpose Q. This is simply the error. Okay. Yeah. So now we have this, and the regret is a summation over LT, and then we also have the regret bound. By the regret bound, we know that this is smaller than 2 times T log of the cardinality of the number of experts, and like just now we've like the left hand side is error and right hand side is regret bound, and just now we've seen that this error needs to be larger than half of alpha, right? So what does it mean? It means that we can also lower bound the regret by T times half alpha. So T times half alpha is smaller than 2 times the square root of T log of the cardinality, and which gives me T is smaller than 16 times log of X over alpha square, right? So this is the result that we get. The number of iterations of running the multiplicative algorithm is small. It is 16 log X over alpha square. So it remains to put everything together. So 2 and 3 tells me that my answers, like suppose my choice of this epsilon is appropriate, it's going to give me everything to be smaller than, so no matter what happens, the output of the accuracy will be smaller than some constant times alpha, right? So check that this is smaller than 1.25 times alpha, and this is smaller than a quarter of alpha. So overall, it's bounded by 5 quarters of alpha, and the number of times we run this multiplicative weight algorithm is smaller than this quantity. Okay, so now like these arguments allows us to choose these parameters appropriately. So first of all, epsilon needs to satisfy again. Epsilon needs to satisfy that this is smaller than a quarter of alpha. So we can take this equation and then choose. Yeah. So let's rewrite it. n epsilon 0 4 log 3k over delta. So this needs to be smaller than 1/4 of alpha. So I can choose epsilon 0 to be 16 log 3k over delta over n alpha. Okay. 3k over delta over n alpha. So how about n? So we also have an inequality about n. We know that this algorithm will stop with this many iterations. So it suffices for us to choose this n to be larger than this quantity. So how about we just choose this n to be the same as this? So we'll choose this n to be 16 log x over alpha square. Yeah. So then what is the total privacy loss? So epsilon total is equal to 2 times epsilon 0 times n, right? So as we've analyzed before, and this is equal to 512 log of 3k over delta log of x cardinality over n times alpha cube. Right, so alpha is a desired error, right? So now we can put everything together into a theorem, which says that with probability at least 1 minus delta, the private multiplicative weight algorithm calibrated to achieve epsilon dp, with epsilon being this epsilon total, and with these parameter choices and with the optimal choice of the learning rate parameter in multiplicative weight, is able to answer any sequence of like Q cardinality, so this is equal to K, linear queries with a maximum error of alpha smaller than 512 log 3K over delta log over n to the, so this is Q cardinality to the power of 1/3, right? And I think we need an additional 1.25 in front because here like we actually have 1.25 alpha, right? So like the cubic root of 512 is what? Is something like definitely smaller than 10, like between 8 and 10, and then multiply with 1.25. So now we have a multiplicative constant factor in front of roughly 10, and it depends logarithmically in both Q and X, and it goes to 0 as n goes to infinity. Yeah, question. Smaller n is size of the data set. Yes, the size of the data set, and this is a bound on the normalized linear queries. Yeah, so comparing to the statistical error, which is order 1 over square root of n, like log Q, right? Comparing to the statistical error, this is like slower. This goes to 0 slower. On the other hand, like this, yeah, I forgot this epsilon parameter. This epsilon needs to be multiplied. Yeah, epsilon is here. Yeah. Move alpha to the left-hand side, move epsilon to the right-hand side, and then take a cubic root. And comparing to Laplace mechanism, the two ways of applying Laplace mechanism, which is Q over n epsilon log of Q over delta, and this another way of applying Laplace mechanism, we get n epsilon but square root of x cardinality and log Q over delta. Right, so comparing to both of them, like this algorithm has weaker dependence on n. It goes to 0 slower, but the dependence on on the number of queries is exponentially better, or the dependence on the space of the data space is exponentially better. Okay. Yeah, any more questions about this algorithm? So we've walked over it like with a lot of details, but yeah, I understand it's a tough algorithm and it's somewhat tricky to analyze as well. And I hope I explained it clearly so you guys now understand how it works. Great. So in the remainder of today's lecture, so I'll spend another like 12 minutes in today's lecture to give you an introduction to the problem private selection, and then I'll talk about one of the most popular algorithm and most general algorithm in differential privacy called the exponential mechanism, and then I'll give the short privacy analysis of the exponential mechanism, which is quite revealing and quite interesting. All right, so the problem of private selection is one that we see like all the time in practice. So the problem setting is easy to state. So we have a set of item in this R. You can think about this as an outcome like output space, and then like each item within this R is associated with a utility function, where this utility function takes a data set and then takes this item and then output some numerical value. And this utility, so the larger this number is, like the better. The larger U is, the more preferred that we are about this item. Okay, why are there privacy concerns? Because if we just want to find the item that maximizes utility, then it reveals information about this data set. Right, so the relative order of these items is a function of the data set itself. So the problem of privacy selection tries to find the argmax of this utility function. Yeah, tries to output R star is equal to argmax of R in this set R, utility of your data and R. So this is a goal. But we can't just output this directly. Due to the privacy concern, so privacy selection like hopes to do this with differential privacy guarantee. So I'll give you a few examples to demonstrate why this is a meaningful thing to do. So take the movie recommendation. Like for example, Netflix wants to reveal the most popular movie, and we have Titanic, Fight Club, and we have say Chongqing Express. Let's say we have 3 items in this R, and then what is the utility function? The utility function of the data set are the Netflix viewers or their users is a number of users who liked this movie R. Okay, then it makes sense that we want to find the most popular movie by the number of people who liked it. The second example, the classical example of learning machine learning classifier. So in this case, this space R is a decision tree 1 linear classifier specified by a parameter theta and theta 1, and the linear classifier with the parameter theta 2 and so on and so forth. So let's say that it's a finite discrete set of classifiers. And what is the utility function? Since we want to maximize it, and this utility function could be, yeah, so X is your training data and R is a particular classifier. So this might be the negative negative errors of sum of I from 1 to n error of this classifier makes on this data point I. Suppose there are n data points, and where we want to maximize the negative error means that we want to minimize the performance of maximize the performance of the classifier on your training data set. So in other words, the empirical risk minimization problem. That's a typical thing that the machine learner would do. And the third example, let's say that in a situation of an auction, and the object space is going to be the price that you're going to sell this item at. Let's say that you have many copies of this CD, and you want to decide like how much to charge for each copy of this CD, so you can maximize your benefit and maximize your profit. So this R is a price to sell an item. So this could be say $0.50, $1, $1.25, $100, and so on. Okay, and how about the utility function? The utility function is measured by say R multiplied with a number of people who's willing to buy, right? Yeah, so this is a number of people who's willing to buy, right? So in this case, like the goal is to maximize the profit or maximize the net revenue, and like in some cases, like we can first find the argmax, right? In many cases, we can first find the argmax, and sometimes it makes sense to do that. In particular, in the learning classifier case, when the classifier is described by a numerical vector of parameters, then we can add noise to the numerical vector, right? Using Laplace mechanism, for example. In the auction case as well, so these actions are prices, so they are numerical values, and we can also think about maybe it's a good idea to add noise to these prices. So that will give you differential privacy. In other cases, say the most popular movie, then the most popular movie is a discrete object, and you can't simply add noise. Like there are no ways that you can add Laplace noise to that, right? And for the auctions in particular, adding noise might have a very bad effect, because if you move this price a little bit higher, then you may get like zero utility. If you move this price a little bit smaller, then it is more stable that way. But the relationship is asymmetric, right? So setting the price to be a little bit larger, say there's just one buyer who's willing to buy at 100, and setting it to be 100.01 will make your utility zero. So that means it's a bad idea to add noise naively to this. So what can we do? So it turns out that we can. So provided that the utility function itself has bounded sensitivity, meaning that for every possible output, and if we add or remove individual data points from the data set, and the utility function is bounded by the global sensitivity delta, then we can run something called the exponential mechanism, which samples from like the Gibbs distribution defined by the utility function itself. So what does a Gibbs distribution mean? You just exponentiate your utility function with epsilon multiplied and divide by 2 times the sensitivity. And what this does is that it makes those more desirable output exponentially more likely, and it makes those items that are not so desirable exponentially less likely to appear, to be selected. Okay, so that's a good idea, because say in machine learning, this corresponds to sampling from the posterior distribution of say a Bayesian model, which comes with all sort of guarantees. And the Gibbs distribution is something fundamental from the information theory perspective. Okay, I'll spend the rest of the lecture, the remainder of the lecture, to give a very short proof of the privacy analysis of exponential mechanism. So first of all, the output is supported on this discrete set or a continuous set. So it suffices, and also we care about the pure DP. So it suffices to bound the probability ratio of 2 neighboring data sets, like giving us the same output. Let's say that there's data set X and X primes that are neighboring. So P of X outputting R over P of X prime outputting R. So let's just write out the probability distribution. So first of all, these probability distribution are proportional to the exponentiated version of the utility function divided by 2 times sensitivity. E of epsilon u x prime r divided by 2 times sensitivity. But that's not the only thing there. There's also this normalization constant, right? So let's also make sure that they are valid probability distribution by dividing both the numerator and denominator by their normalization constant. Over 2 delta. Okay, and this is divided by r tilde of r e to the power of epsilon u x prime r tilde over 2 delta. Okay, now we'll handle like the two ratios separately. For the first ratio, and we can combine them together, and we'll have epsilon 2 delta and u x r minus u x prime r, right? This is smaller than e to the power of half epsilon by the fact that the absolute value differences, but by the fact that the sensitivity of this utility function is smaller than delta. Now, for the second term, we'll deal with this one. Okay, flip this to the numerator. So we'll have r tilde in a range space e to the power of epsilon u of x prime output r tilde over 2 delta. So I'm gonna subtract u of x r tilde and then add it back. Okay, and this is divided by r tilde plus r e to the power of epsilon over 2 delta and u of x over r tilde. Okay, so what we can do is to group this part of this exponential together and apply the sensitivity of the utility function. And this is smaller than I guess e to the power of 2 epsilon. I'll copy this and then I'll extract every one of these product with a maximum value. So I'll get sum of r tilde in the range e to the power of half epsilon again, and then multiply with e to the power of epsilon u x divided by e to the power of 2 delta epsilon u x r tilde, right? And this is a constant that I can extract it out, and everything else will cancel out, and this gives me e to the power of epsilon. So that concludes the proof for the epsilon dp of exponential mechanism. Okay, so this is where we're gonna stop today. So I'll talk about the connection between exponential mechanism to randomized response and Laplace mechanism. I'll talk about its utility analysis and talk about other ways of doing differentially private selection, as well as making a start on advanced composition in the next lecture. Yeah. Thank you very much for coming.